Welcome back to our course, Fundamentals of Operating Systems, based on the text Operating System Concepts, 10th edition, by Abraham Silberschatz, Greg Cagney, and Peter Galvin, published by Wiley Publishing. In the last two lessons, we've been discussing CPU scheduling algorithms. We examined the first-come, first-serve algorithm, and then in the last lesson, we evaluated two of them, shortest job next, both the non-preemptive version, shortest job next, and the preemptive version, shortest remaining time. In this lesson, we're going to examine the round-robin CPU scheduling algorithm. So let's begin. The round-robin scheduling algorithm is like first-come, first-serve, but it is preemptive to enable the system to switch between processes. A small unit of time, called a time quantum or a time slice, is defined. A time quantum is generally from 10 to 100 milliseconds in length. The ready queue behaves like a circular queue. The CPU scheduler goes around the ready queue, allocating the CPU to each process for a time interval for up to one time quantum. To implement round-robin scheduling, we again treat the ready queue as a first-in, first-out queue of processes. New processes are added to the tail of the ready queue. The CPU scheduler picks the first process from the ready queue, sets its timer to interrupt after one time quantum, and then dispatches the process. One of two things will then happen. The process may have a CPU burst of less than one time quantum, in which case the process itself releases the CPU voluntarily. The scheduler will then go to the next process in the ready queue. If the CPU burst of the currently running process is longer than one time quantum, the timer will go off and will cause an interrupt to the operating system. A context switch will be executed, and the process will be put on the tail of the ready queue. The CPU scheduler will then select the next process in the ready queue. The average waiting time under round-robin policy is often long. Consider this set of processes that arrive at time 0 with the length of the CPU burst given in milliseconds. If we use time quantum of 4 milliseconds, then process 1 gets the first 4 milliseconds. Since process 1 requires another 20 milliseconds, it's preempted after the first time quantum, and the CPU is given to the next process in the queue, process 2. Process 2 does not need 4 milliseconds, so it quits before its time quantum expires. The CPU is then given to the next process, process 3. Once each process has had one time quantum, the CPU is returned to process 1 with another time quantum. Therefore, the average waiting time is 17 divided by 3, or 5.66 milliseconds. In the round-robin scheduling algorithm, no process is allocated to the CPU more than one time quantum in a row, unless it is the only runnable process. If a process's CPU burst exceeds one time quantum, that process is preempted and is put back in the ready queue. The round-robin scheduling algorithm is therefore preemptive. Each process gets an equal share of the CPU's time in chunks of whatever the size of the time unit. Each process must wait no longer than the number of jobs times the size of the time units until it next gets the CPU. For example, with 5 processes and a time quantum of 20 milliseconds, each process will get up to 20 milliseconds every 100 milliseconds. The performance of round-robin depends heavily on the size of the time quantum. At one extreme, if the time quantum is really large, the round-robin policy is the same as the first-come, first-served policy. On the other hand, if the time quantum is very small, say 1 millisecond, the round-robin approach can result in a huge number of context switches, and a context switch, as we have already learned, is time-consuming. You know, it's got to save that process control block, bring the other process control block in, and so on. Assume, for example, that we have one process of 10 time units. If the quantum is 12 time units, the process finishes in less than the time of one quantum with no overhead. If the quantum is 6 time units, then the process requires 2 quanta, resulting in a context switch. If the time quantum is 1 time unit, then 9 context switches will occur, slowing the execution of the process accordingly as shown in this figure. So we want the time quantum to be large with respect to the context switch time. If the context switch is approximately 10% of the quantum time, then about 10% of the CPU time will be spent in context switching. In practice, most modern systems have a time quantum ranging from 1 to 100 milliseconds. The time required for a context switch is less than 10 microseconds. Therefore, the context switch time is a small fraction of a time quantum. Let's take a break, look over your notes, and in the next video we'll continue with our investigation of the time quantum.